Assalamu alaikum. I'm your instructor Nimra Zafar for the subject of architectural structures. Today we will study shell structures. So this is a basic geometrical shape of the shell structure. It is a thin membrane structure. You can see in the picture as well. So this is a big shell which is usually used in the roofs or in overall structures in the bigger structures where we cannot afford other structures like frame or concrete structures, frame structures or trusses. There we use shell structures. These shell structures are made of concrete or glass, or there are other such materials which are very thin membrane type. And this thin membrane is basically lightweight, but it supports huge load. So let's go into the detail what the shell structures basically are. Introduction of the shell structures. Lattice and portal frame buildings consist of a structural frame which supports slab, roof, and wall covering. This frame serves purely as the structural support and provides protection against weather. The roof and wall coverings add nothing to the strength and rigidity of the structural frame. A shell structure is a thin, curved membrane or a slab, usually of reinforced concrete, that functions both as structure and as covering. What conventionally happen? We have walls, and then we have roof, floor. We have different structural systems which are connected to one another to make a structure. So the purpose of the roof and the exterior is to provide protection against weather and also to provide structural support. If we have any covering on the roof and wall, it will do nothing to the strength or rigidity of the structure. Rather, it will only provide a covering against weather, or it acts as a shielding material. This happens conventionally. So, if we talk about a shell structure, it is a thin curved membrane. Basically, it is in the curved shape, bended or in the curved shape. Uh, it is usually of the reinforced concrete. Reinforced concrete means that it is of concrete and there is reinforcement of the steel bars provided inside it to increase its strength. It is thin and the strength is provided with the help of reinforced concrete that functions both as structure and covering. So there are no separate walls or no separate roof. There is a single curve which act as a roof as well as wall, and it plays function of both providing the structural support and providing the covering, exterior covering. The term shell is used to describe the structures which possess strength and rigidity due to its thin, natural, and curved form, such as shell of an egg, a nut, human skull, and shell of tortoise. Okay, Jeet? Um, it's basically its strength or its rigidity is because of its thin structure, its thin shell, which is very light in weight and which is uh, acting both as structure and as the covering. It is on the basis of the concept of an eggshell, human skull, then shell of a tortoise. This is the seashell. This is again a seashell. So these all of these are thin shells which are structurally very strong, and they provide the other function, their respective functions, like the purpose of the eggshell is to protect the egg yolk or egg white inside it, and the human skull, the human bones, or the mass of human body inside the brain. So all of these things have their respective functions. These shells are very thin. All of these perform their respective function. They have their strength due to their thin membrane type material. So the cell structures are basically made on this concept that they are thin, lightweight, have provide structure support as well as other play their role as covering of a barreling. Then we have single or double curvature shells. Single curvature shell. Let's see what single curvature shell is. Single curvature shells are curved on one linear axis and are a part of a cylinder or a cone in the form of barrel warts and conite shells. Okay, as the name suggests, in single curvature shell we have a single curve on one axis, linear axis. This is our linear axis, straight linear axis. So we have one curvature along that linear axis, and if we talk about the barrel warts and canals, so these shell structures are basically in the form of cylinders or cones. Then we have double curvature shells. They are either part of a sphere or a hyperboloid of revolution. So these two are geometrical shapes, sphere and hyperboloid. So double curvature is the part of these shape. Double curvature has two curvatures, one on this side and one on this side. The terms single curvature and double curvature do not provide a precise geometric distinction between the form of a shell because a barrel wall is single curvature, but so is a dome. Okay, so with the help of shape, it is very difficult to distinguish between the curvatures, single and the double curvatures, as barrel vault is single curvature and the dome itself is a single curvature, but we see the dome round from all the sides. Domes come in single curvature, but it is curved from all the sides. So if it is curved from all the sides, we will not say that it is double curvature. It is single curvature. Single or double curvature uh, shells. The terms single and double curvature are used to distinguish the comparative rigidity of the two forms and complexity of centering necessary to construct the shell form. The difference between the single and the double curvature is that uh, uh, there there is the difference of their rigidity uh, depending upon their shape. So if this we have this parallel wall, this is single curvature, and this is our axis, and this all arc is constructed on this axis along this linear axis. Then in canard, again we have this single curvature along this linear axis. Then we have hyperboloid. In hyperboloid, we have one curve along this axis and one downward curve along this axis. This curve is spread along this axis, and this curve is spread along, this is downward curve, this is spread along this axis. Then we have dome. In dome we have curves from all the four sides. One curve, two curve, three curve, four curve. Then we have forms of curvature and then their surfaces of revolution. Surfaces of revolutions are generated by the revolution of a plane curve called the meridional curve. So this is plane along which we can revolve a body. Okay, there is an axis or the plane along which we can rotate or revolve a body. That rotational curve is called meridional curve. How- And if the axis along which we rotate or revolve the surface, that axis is called axis of revolution. In the special cases of cylindrical and conical surfaces, the meridional curve consists of a line segment. Sometimes it is a point, and sometimes in cylindrical and conical surfaces, it is a line segment. It is a straight line, whether it is horizontal or whether this is this way. Vertical. In examples, we have cylinders, cones, spherical or elliptical domes, hyperbolas of revolution, and toroids. So if you see the circular cylinder, we have this line of revolution, axis of revolution, along which this circular cylinder will revolve. If you talk about the cone, we have this axis of revolution along with the cone will revolve. For hyperboloid, we have this axis of revolution, and this axis of revolution is also called as meridional curve. Plane, basically the plane along which it revolves is called meridional curve. So these are meridians. This is the plane along which it will revolve. Meridian. This is toroid. This is axis of revolution, and this is the its meridian along which it will revolve. Then we have surfaces of translation. Surfaces of translation are generated by sliding a plane curve along another plane curve while keeping the orientation of the sliding curve constant. The later curve on which the original curve slides is called the generator of the surfaces. In the special case in which the generator is a straight line, the resulting surface is called cylindrical surface. Okay, what happened in translation? One surface or one plane curve slides against another curve, but the orientation remains constant. The curve at which the original curve meets the later curve along which the original curve meets is known as generator of the surface, which is basically generating a revolution or translation. If the original curve is striking another curve, it is generating a translation, or and this curve is called the generator of the surface. In some special cases where generator is a straight line, not a curve, the resulting surface is cylindrical surface. Okay, now you can see the surfaces of translation with a rectangular plan. So this is first example of an elliptical paraboloid. This is cylindrical paraboloid. You can see this shape. And this is hyperbolic paraboloid. So this is one curve. You can see this. And this is an other curve. These two curves are striking each other or meeting each other to create surface of translation, to create a new surface. Then we have this curve and this curve. So these two curves are meeting. They have different curvature. These two curves are meeting and creating a new translational surface, or you can generate call it. You can call it generator surface. Then you have one curve this way and one curve this downward way. So their curvature is different, and the two curves are combining together to create a new generator, or to create or generate a surface. So it will be called as generator surface. Two parabolas are similar, the surface becomes a surface of revolution called paraboloid of revolution. If this is this surface and the other surface is same, it will be called as paraboloid of revolution or surface of revolution. See, we have one concave parabola and another concave parabola. If they two combine, so they form a dome. Then we have one concave parabola and one convex parabola. They combine and they both form hyperbolic paraboloid, whose one curve is upward and the another is downward. Then we have ruled surfaces. Ruled surfaces are generated by sliding each end of a straight line on their own generating curve. These lines are not necessarily at right angle to the planes containing the end curve. So what is happening in ruled surfaces? Basically, these straight lines are producing curve. So you can see an example of cooling tower. It has straight lines and they are creating a curve. This curve, this curve, this curve. These two curves are generated by all the straight lines. So basically, the straight lines are um, creating a sliding with each other and they are generating curves. And it is not necessary to be for these lines to be at right angle to each other. Then there is an example of conoid in which again there we have straight lines and they are generating a curve, and they are not at necessarily at they are at right angle, but these lines are not at right angle to each other. Conoid generated by a straight line traveling along another straight line at one end and curved line at the other end. This is a curved line and this is the straight line. So straight lines are starting. These straight lines are started from this straight line and they are meeting the curve on the other end. Then we have shells. They are singly curved and doubly curved. For singly curved shells, we have developable shells which have further two types: surfaces of revolution and surfaces of translation or ruled surfaces which we have studied or earlier. Surfaces of revolution include circular cylinders, barrels, or cones, and surfaces of translation or ruled surfaces include circular or non-circular cylinder and cone. Then we have doubly curved or non-developable shells, which includes synclastic or anticlastic. Synclastic further include surfaces of revolution and surfaces of translation. Surfaces of revolution include circular domes, ellipsoid of revolution, paraboloids of revolution, and surfaces of translation include elliptic paraboloids and paraboloids of revolution. In anticlastic, we have surfaces of revolution as have hyperboloids of revolution of one sheet, and then surfaces of translation. In this, we have hyperbolic paraboloids, conoids, hyperboloids of revolution of one sheet. Now let's see what are the developable and non-developable surfaces. Surfaces with double curvature cannot be developed, while those with single curvature can be developed. So developed surfaces we have the double curvature single curvature surfaces which are developed, while With double curvature, they are non-developable. It is the name given to them. This is the single curvature uh, or single curve structure, which we call it as developed. And then we have this non-developed in which we have multiple curvature. In this again we have multiple curvature. In other words, surfaces with positive and negative Gaussian curvature, that is synclastic and anticlastic surfaces, cannot be developed, while those with zero Gaussian curvature can be developed. So if we have positive and negative Gaussian curvature, that means it is this way, upward curvature and downward curvature. Synclastic and anticlastic, they cannot be developed. They are double curvature. While those with zero Gaussian curvature, which have only one curvature, they can be developed. Now here we have types of Gaussian curvatures. This is positive Gaussian, which is upward curve. Then we have zero Gaussian, which is curved from this side as well. From this curvature is extended. Here we have straight line here and we have curvature here. But here we have curvature here as well as this curvature is also extended. Then we have negative Gaussian where we have this curvature upward and this curvature downward. This is bent downward. Then we have developable surfaces, which are singly curved surfaces. The other name is singly curved surfaces. Developable surface is a surface that can be unrolled onto a flat plane without tearing or stretching it. If we unroll a developable surface on a flat plane, it is unrolled without any tearing or having a stretch in it. It is formed by bending a flat plane. The most typical shape of a developable shell is a barrel, and a barrel shell is found only in one direction. Then we have barrel. Arch action and beam action together make a barrel. There are mainly of two types: long barrels where arch action is prominent, and then short barrels where beam action is prominent. So what happens in barrel? We have one arch and a beam. We have one arch and then a beam which is extended. So this is an arc which is extended as beam. Sorry for the drawing. This is beam and this is arch. And what happens in long barrel? Barrel action is prominent. What happens in short barrels? Beam action is prominent. Structural behavior of short barrel shells. These shells are typically supported at the corners and can behave in one of a combination of the following ways. These are the ways in which the corners, the short barrels behave. These are the ways. In any of the following ways, short barrel will be. Then we have structural behavior of a long barrel shells. These are typically supported at the corners and behave structurally as a large beam. In long barrel, our beam action is prominent, so they are supported at the end and structurally behave as a large beam. Whereas in short barrel, arch action is prominent, and we have the following possibilities of the behavior. So these straight lines or these solid lines show compression, and this dotted line shows tensions. This is a long barrel which is acting as a beam. So it is in compression this way, and it is in tension in these particular parts. As beam top part of the beam is in compression and the bottom one is in tension, the same happens in the long barrels. The top part of the shell is in compression, compressive force is dominant there, and the bottom part is strong in tension. The forces are pulling apart. Then in short barrels, arch action is prominent. So we have forces which may be acting this way. We may have forces which may be acting this way, or we have may have forces acting this way and this, right? Then we have non-developable surfaces which are doubly curved. For example, sphere or hyperbolic paraboloid. These are mainly classified as synclastic or anticlastic. Synclastic. These shells are doubly curved and have a similar curvature in each direction. Synclastic are doubly curved, for example, domes. Now, previously it was saying as that the domes are singly curved and their curvature is in all the four sides. But now, if we go in the detail, while talking about synclastic and anticlastic shells, we have dome in synclastic curves which are doubly curved. We have two curves in that, one from the horizontal plane and one from the y plane, one from x plane and one from y plane. A dome is a good example of synclastic shell. It is doubly curved and can be formed by rotating a curved line around an axis and hooped line. A dome can be split up into two different directions. Vertical section separated by longitudinal arch line, also called meridians, and horizontal section supported by hoops or parallel. So there are two directions, vertical sections in which are separated by arches longitudinal in the longitudinal direction, and they are also called as meridians. And then we have horizontal sections which are separated by parallel. The structural behavior of the dome is or the synclastic curvature is similar to arches under a uniform loading. The dome is under compression everywhere and the stresses act along the arch and the hoop lines. So this is a dome which is synclastic. We have one curvature this way and the other curvature this way. Then we have non-developable surfaces, anticlastic. In cyclistic, there was double curvature and that was similar in both the direction. Now in anticlastic, we have double curve, but each of the two curves have the opposite direction to the other. In cyclistic, we had uh, two curves, but they were in the same direction. In anticlastic, as the name suggests, anti, we have two curves, but they are in the opposite direction. For example, saddle points. Conides, hyperbolic, parabolite, and hyperbolites are all considered to be anticlastic shells because they are similar shape with different curvature in each direction and straight lines can be drawn off the surface. So you can see the example of conides. Conides are formed by moving one end of a straight line along a curved path and the other along a straight path. So one end along a straight path and the other along a curved path. So this is a conide which is anticlastic. This curvature is upward and this is here we have curvature, not curvature, straight line. Basically, these two are examples. Hyperbolites are formed by rotating a straight line around a vertical axis. So this is a straight line. We are rotating this straight line along the vertical axis. Or by sweeping a straight line over a straight path at one end and another straight path not parallel to the first. So what's happening? We have one concave parabola and one convex parabola. We basically swap those parabolas, one concave and one convex. Structural behavior. Depending upon the shape of the shell relative to the curvature, there will be different stresses. Shell roofs have the compression stresses following the convex curvature and the tension stresses following the concave curvature. So what happens in the shell roofs? We have the compression forces acting upon the convex side of the curvature, and we have tension forces acting upon the concave side of the forces. Okay. These are different forms of the anticlastic curvatures where we are basically rotating the straight lines. These straight lines are rotated along the vertical axis. Ancient tie. So the figure given below is represents a doubly curved shell with no axis of symmetry. Shows a spherical dome supported on a wall. Whenever the shells are supported vertically at their edges, a tension tie is required around the perimeter at the intersection of the dome and the wall. So this is a wall and this is a dome. We have supported this dome on the wall and we have a tension tie to basically connect these two things, dome with the wall. However, it is important to note that the tie will be funicular for any shape of either the plan or the elevation. Figure B shows the shell has positive curvature and the continuous vertical support. So this is the positive curvature, upward curvature. Then there is the supporting wall, and we have a tie to support this curvature with this wall. The support may be a continuous wall or a stiff beam between adequately spaced columns. It is intersecting the straight parts of the tie in the figure C and it does not require ties across the building. thrusts are taken by shear forces through the width of the shell, and only tension forces exist in the tie. Okay, all the shear forces are taken through this width of a whole massive shell, whereas we provide the ties to support the this curvature on the walls or on any other support columns, or tension forces are basically taken by the ties. Shear forces are taken by its massive width of the shell, and tension forces are taken by the ties. So this is a cylindrical shell combined with the spherical shell. This is cylindrical shell and this is spherical shell. And there are columns and beams. These are the columns and this is the beam. And we have provided the tension tie here. Like it will be somewhere here. So that's all for today. Thank you very much for hearing.